Good afternoon, Extension 2. Welcome to your first online 3D vectors lesson. As always, we're going to kick off with a revision question based on what we've been doing recently. So we need to find a vector which is parallel to the vector 2, minus 3m as our x, y, and z components, and it needs to have length of pi units. We're going to leave our answer as a column vector, and it's going to be in terms of m because m is unknown. So pause the video and have a go. Solution's coming in 5 seconds. And here is our solution. So first thing we need to do is find the length of vector v by taking the magnitude with a cheeky bit of three-dimensional Pythagoras. That works out to be the square root of m squared plus 13. Now if we take vector v and we divide it by its length, which is the same thing as multiplying by 1 over the length, this now turns it into a unit vector with length 1. Okay, so this is the unit vector parallel to v, and we write that as v with a little hat on. Okay, so if this vector has length 1, if we multiply it by pi, it now has length pi. So I'm just going to call this vector u, and this is our answer. Okay, we're just going to write this as a column vector, which means we've got pi divided by square root of m squared plus 13 times 2 for the x component, times minus 3 for the y component, and times m for the z component. And there's your answer. Okay. So for today's lesson, we are looking at the vector equations of curves. And this is involving parametric equations, which you would have seen in Extension 1 towards the end of last year. Hopefully it's vaguely familiar. Okay, we're going to kick off. We've got, first of all, we need to talk about how to find the equation of a sphere in 3D. Okay, so I'm sure all of you remember that the equation of a circle with radius r and center hk is given by x minus h squared plus y minus k squared equals r squared. Okay, and we derived that formula in year 11 using Pythagoras. And as we looked at before, Pythagoras still pretty much works in 3D. You just have to do it in 2 directions, but you do end up with a Pythagorean equation. So we can apply this logic and find a sphere equation, and it's exactly what you would expect. Okay, it's just the exact same as a circle equation, but now we just have a z component to make it 3D. Okay, so this is a 3D sphere, radius of r, and center of HKL. Okay, that three-dimensional coordinate, I suppose. So a couple examples using this concept. First of all, we have, here is the equation of a sphere, because we have x squared, y squared, and z squared. I want you to find the center and radius by doing a case of triple completing the square. Okay, so you can probably pause this one, have a go if you want, but if you're not sure where to begin, we'll go through it now. So like I said, we're basically just doing 3 cases of completing the square. So it's going to look like this. Okay, just moving the plus 2 across to make negative 2 just makes it a bit more simple. And now we put the x squared with the 4x, and we put the y squared with the minus 3. Oh, sorry, yeah, minus 3y. And we put the z squared with the plus 2z. Okay, now we say to ourselves, well, half of 4x is 2x, or half of 4 is 2. Square that is 4, so we'll add that to both sides. Okay, the one in the middle is a bit tricky because half of negative 3 is negative 3 on 2. And then when you square that, you get positive 9 on 4. So we'll add that here and add that here to complete the square. And then this one just needs to add 1 to both sides. And now if you've done that correctly, you have 3 perfect squares, which you can factorize to make look like this. Okay, we have x plus 2 squared here. We have y minus 3 on 2, the thing that we squared. And we have z plus 1 squared. And this on the right works out to be 21 over 4. Okay, so from that, we can just see from inspection that our center needs to be minus 2, positive 3 on 2 for y, and negative 1 for z. And if this is our radius squared, then the radius will be the square root of 21 over 4, which works out just be root 21 on 2, square root of 4. Okay, so there's our answer, pretty straightforward. Next example is a little bit trickier. We have, given that these 2 spheres, so we have a sphere with radius 3, center at the origin, 0, 0, 0. And we have a sphere with radius 4, center at 0, 0, 4. Given that these 2 spheres sort of overlap and intersect, we need to find the values for z where they intersect. Okay, so as with any question like this, when we're asked to find where to functions or relations or whatever intersect, usually that involves solving the two simultaneously. So that's what we'll be doing here. We're going to set up equation 1 as the first sphere, and the second sphere we're going to call equation 2. And now luckily we have x squared and y squared matching up. So if we just do the second equation, take away the first equation, those x squareds and y squareds are going to vanish, and we'll just get z minus 4 squared, take away z squared equals 16, take away 9. Okay, so working that all out, we can expand the perfect square here and do z squared minus 8z plus 16, still with the minus z squared here. 16 minus 9 is of course 7, if my math is correct. And now we can do z squared take away z squared, gives us nothing, doesn't it? And then we can take 16 from both sides and just leaves us with negative 8z on the left, and on the right we'll do 7 take away 16 and get minus 9. Okay, now we just solve by dividing by negative 8 and we get z equals 9 over 8. Okay, so what that means is that in this three-dimensional plane, as long as the value of z is 9 over 8, it doesn't matter what the x and y values are, these two spheres are going to be colliding, okay, or overlapping, really. So that is the value of z where these two intersect. And now for the second part, we're going to find the equation of the circle in which they intersect, okay? So what that essentially means is taking these two three-dimensional sphere equations and turning them into circle equations using the fact that we now know the value of z, okay? We just solve for that. And like I said, where z is 9 over 8, these two spheres are overlapping. So you can pick one of the two equations, it doesn't matter. I'm going to pick equation 1 because it's a bit simpler, and I'm just going to substitute in z equals 9 over 8, which means that z squared will be 9 squared over 8 squared. Now if we just subtract that over the other side, we get a circle equation. We get x squared plus y squared equals what works out to be 495 over 64. Okay, so that is the circle. Try and picture it in your head. You've got two spheres that are overlapping, and you're trying to find the circle that sort of spans the area that they overlap. Okay, yeah, it's a bit of a brain buster, but there is our solution. That is the equation of the circle. All right, for the next part of this lesson, we're going to be looking at how we can use parametric equations to describe curves and lines in the 3D sphere with vectors. Okay, so for example, just to sort of give you an idea, an object is moving through the IJ planes. This one's just two-dimensional to give you just a warm-up. Its position at time t is given by the vector, so vector r as a function of t is equal to 3 minus t times I plus 2t times j. Okay, so what this means is we essentially have a function where if we sub in a t value, we get an answer for an x and a y, and it gives us a position. Okay, so here's just a table of some t values being subbed in. So if we sub in 0, we get 3 minus 0, which is 3. So we get 3i plus 2, 0, so we get nothing. Okay, so we get 3i as a vector, which points to the coordinate 3, 0. Okay, because this is all going to give us position vectors from the origin. All right, if we sub in 0.5, we get 2.5 here and we get 1 here. So we get this vector, which points to this coordinate. Okay, likewise, if you subbed in 1 and 2, you would get these two vectors pointing to these two coordinates. All right, so if you map these out on an axis, you get this picture. Okay, shout out to New Senior Mathematics text for these diagrams. So what we have here are our four vectors, R0, R0.5, R1, R2, okay? And if we join together all the points that these vectors are pointing to, we get a line. Okay, so parametrically, this function is representing this family of vectors, I suppose, which in essence point towards this line. Okay, and as you can see, this is just a linear function. It's got a y-axis intercept of 6. It's got a gradient of 6 over 3 is 2, so it's minus 2. So if this is our parametric equation, then we can say, well, the Cartesian version is negative 2x plus 6. Okay? So today we'll be doing a lot of practice of going between parametric vector equations and Cartesian equations, which are hopefully both describing the exact same thing. Okay? And we can see that here. If we take our vector function, r of t, and we isolate the x and y components, we have x is equal to 3 minus t, and y is equal to 2t. Now we can sort of combine these together and make a Cartesian equation like we did in extension 1. Okay, we can rearrange the x and say, well, if x is 3 minus t, if we take the t over and then minus the x over, we get that t is equal to 3 minus x. Now we can substitute that into the y equation and say, well, if y is 2 times t, it's going to be 2 times 3 minus x. And then voila, you have a Cartesian equation. So Cartesian means x and y coordinates. Okay, we can expand it out and we got the exact same function. Okay, so that's how this works. Here is a function with an extra parameter, which is usually t or sometimes theta, whatever. This sort of produces a family of vectors, which in turn point to this line, is how my brain sort of makes sense of it. Okay, so we'll try a few more examples. Luckily, most of these examples are going to be more algebra-based than sort of concept or graphical-based. Luckily, the Extension 2 syllabus doesn't specifically mention any sketching of 3D functions or lines, because obviously it's very difficult to do properly. So I would say if there's any 3D sketches or lines in your assessment, I'd say they'd be given to you and you'd be interpreting rather than producing your own. Okay, so today we'll be focusing mainly on sort of algebraic methods. So first of all, we have a curve being described by x equals t plus 3 and y equals t squared minus 5. Okay, so the vector equation for this curve is going to be what we're just doing. Okay, we have an x component and a y component, so we just write it in a vector form. Okay, so instead of xi and yj, we have x and y in terms of our parameter. Okay, that's all this means. This is the vector equation for the curve that's described by these parametric equations. Okay, now for the actual maths is find the Cartesian equation. So again, this is a pretty simple one, reminiscent of extension 1. We are just combining these two equations together to have a function that's only in terms of x and y. Okay, so hopefully you can see what needs to be done here. We're going to rearrange this first equation and we're going to substitute it into the second one. So if x is t plus 3, it means that t is going to be x minus 3, just taking the plus 3 across. And now, like I said, we're just going to substitute that into the second parametric equation. So if we have y equals t squared minus 5, we have y equals x minus 3 squared minus 5, because this is now t. Okay, there is your answer. That's a Cartesian equation. We can just expand it and tidy it up to get a better answer and end up with, so we have the expansion of x squared minus 6x plus 9, and then plus your 5 gets you a plus 14. And there's your answer. We'll do another one. This one's a bit more tricky. We have a curve described parametrically by x equals 3 cos theta and y equals 3 sine theta. Okay, so this one's a bit more sort of, you have to know what you're doing, I would say. If you remember this from extension 1, you may recognize these as the parametric equations for a circle. Okay, and we'll get to why that is later. But first of all, the vector equation, just again, is very straightforward. It's just a vector with x and y components given by x and y here. So once again, we're just going to write r for our vector equation function. We have I and j, where the x component and y component are the parameters. 3 cos theta and 3 sine theta. Okay, now the involved part is combining those two Cartesian equations, combining the two parametric equations to form a Cartesian equation. So the way we handled this in extension 1 is you can't really easily rearrange this for theta and then sub this into y. So the way we work around this is we take both of the parametric equations, x and y, and let's just square them. So we get x squared equals 9 cos squared theta, and we get y squared equals 9 sine squared theta. The reason we did this is because now when we sum those two together, we end up with x squared plus y squared equal to 9 cos squared plus 9 sine squared. And of course, you can see where I'm going here. We factor out the 9, and then cos squared plus sine squared is, of course, just 1. So we end up with a circle. X squared plus y squared equals 9. Okay, we're going to do a couple more trigonometric ones. So for the next two, we're going to do, so here we have the parametric equations in terms of, for the first one, we have a parameter of t. And we're going to find the Cartesian equation. So once again, we need to try and combine these two separate parametric equations into one Cartesian one. Okay, so we'll kick off with that one. All right, so we have x equals 2 cos t and y equals root 3 sine t. So this is very similar to the last one, except we have constants in front of these two. So the way we're going to handle those is we're going to just get rid of them. So I'm going to move this 2 under here and move this root 3 under here, like this. Okay, now that we have x over 2 equals cos t, and we have y over root 3 equals sine t, now again we can just square both of these equations. So we get x squared over 4 equals cos squared t, and we get y squared over 3 equals sine squared t. Now once again we can add these two equations together, because sine squared plus cos squared, no matter what the variable is always going to be 1. So we get our answer of x squared over 4 plus y squared over 3 equals 1. Now, for thinking about what that looks like, this used to be a large part of extension 2 that's recently been removed for the new syllabus, but that is actually an ellipse. If you want to have a picture of it, it looks like this. Okay, so x squared over a squared plus y squared over b squared equals 1 is an ellipse where the height is b, half the height is b and half the width is a. So this ellipse here would have a height of from 0 to 2, and its width would go from 0 to root 3. Okay, but you aren't expected to know that, but it's just good to know. For the next one, we have x equals cos 2 theta and y equals cos theta. This one looks kind of confusing at first, but it's actually very simple as long as you can look at cos 2 theta and you know the different forms for that. Okay, there was 3 different identities for cos 2 theta. One of them was cos squared theta minus sine squared theta. One was 1 minus 2 sine squared theta. But the one that's useful for us today is that cos 2 theta is equal to 2 cos squared minus 1. Why is that convenient? Well, because we know what cos theta is. It's y. So if we're trying to put these two together, we're going to write x as 2 cos squared minus 1, because then this 2 cos squared is really just 2y squared. And there you go. There is your parametric equation. It's just it's y squared, so it's going to be a sideways parabola, isn't it? All right, and to finish off today, we've got 2 more. A little bit more challenging. Well, they look more challenging. They're not actually too bad. So again, we have vector equations here. So here is our x component and here is our y component. We want to go from that information to a Cartesian equation. So as I said, we have our x and our y. Now we have to think about how could we combine these two. Well, you may notice that we have plus 1 over t and minus 1 over t. So a good instinct would be to, well, if I just plus these two together, these two terms are going to vanish. So if we do x plus y, we just get t plus t, which is 2t. Okay, which is not great because we still have a parameter. We just want x's and y's, but we're getting there. Because now we can say, well, if x plus y is 2t, we can divide by 2 and get the t is equal to x plus y over 2. Okay? Now what we can do is we can substitute this into one of these two equations and there'll be no t's. I'm going to take the y equation, just because I felt like it, and I'm going to change the t to an x plus y over 2, which means that the reciprocal of t will be 2 over x plus y. So that is a correct answer. That is a Cartesian equation. We're just going to tidy it up a little bit because it's very messy. So we're going to get rid of the fractions by multiplying each term by 2 times x plus y. So if we multiply everything to eliminate the fractions, we get this. Okay, I've done the left-hand side multiplied by 2x plus y. I've done this multiplied by 2 to cancel that, and we get x plus y squared. And here we have 2 multiplied by 2x plus y. So we end up with this. Okay, now we just need to expand it all out. So we get 2xy plus 2y squared. We get x squared plus 2xy plus y squared, and we have minus 4. Almost there. We can cancel the 2xy's, take them away from both sides. We can take y squared off both sides, and we end up with x squared minus y squared minus 4 equals 0, which means that x squared minus y squared is equal to 4. Okay, which again, the equation looks like a circle because we have x squared and y squared. What happens when you have a negative in between them instead of a plus is, well, what I say is that the circle turns inside out. And if you want to see what an inside-out circle looks like, it's this. It's called a hyperbola. You're used to seeing them through here and here, but it's the exact same shape, just rotated. So instead of going through here, it's going through here. Okay, again, you're not expected to know that, but it's just a bit of trivia so you can understand what that looks like for future reference if needed. All right, and the very last one for today, we have, again, a vector function, x component here, y component here, parameter is t. We want to try and get a Cartesian equation with just x and y. So we're going to write down our x and y components. Now this one is similar to the last one, except instead of t plus 1 on t, we have t squared plus 1 on t squared. All right, that's going to make our approach for these two very different because these two are very different, okay? We can't add these two together and get rid of anything because these are all squareds and these are all single terms. So what we're going to do is, saying that these two are different, we're going to try and make them look more similar by taking the x equation and squaring it. Okay, squaring both sides. So don't write t squared minus 1 over t squared, that's wrong. You're going to do a perfect square. So we end up with t squared. If we multiply these two terms together, we get 1. So we times it by 2 and put the negative. And if we square this, we get 1 over t squared. Okay? Now that's actually way better because now this equation and this equation are pretty similar. They both have t squareds and they both have 1 on t squareds. All right, so if x squared is equal to t squared plus 1 on t squared minus 2, well, in the setup, t squared plus 1 on t squared is just y. So really, this can just be written as x squared equals y minus 2. Or if you prefer, we can write y equals x squared plus 2. Either way, it should be obvious that that is a parabola, and it's a Cartesian equation, only y's and x's, no t's. So we have completed the question. All right, so that's it for today. If you want some more practice with these types of questions, you can look up 3.4 and 3.5 in the new senior mathematics textbook. That's from 96 to 100, that's online. Or if you want exercise 5.5 in Howard Mathematics, is not as in-depth, but still some good questions in there. So you can pick either of those, or if you're super keen, you can work through both. And that should do you guys for this week. Okay, thanks for watching. I'll be in touch soon. Bye for now.